Hello guys, welcome back again. My name is Amit and it's code time. So we are back again with part 2 of the DSA lecture series, just continuing with time and space complexity. So as we said that in this part, we'll be talking about the notations that we use, the big O notation, the omega notation and the theta notation for average case complexity, best case complexity and the worst case time complexity and the rules for calculating time complexity. And we'll be going through with some examples and calculating their runtime and seeing, what we hold. Okay, so without wasting any time, let's start with part 2. Okay, so yeah, we'll continue from here onwards. So as we discussed in last video, that we know now why don't we use a proper machine based runtime, right? Because it can be deceptive, as different machines will require different amount of time to run different algorithms, the same algorithm. That is why we needed a what we needed an unbiased standard for calculating, for measuring the runtime. And that's why we move on to the big O notation. We move on to the big O notation. Okay, so basically, what this big O notation means, it is basically a mathematical function that is defined in terms of input size. Okay, what is this mathematical function? Okay, suppose you have an algorithm. Okay, suppose you have an algorithm A1 and it takes some number of steps to execute. Okay, it takes some number of steps to execute. We basically want to calculate, the number of these steps. See, as we said, as the number of steps increase, number of steps when increase, your runtime would also increase. Okay, it is proven, right? If you increase the number of steps in your algorithm, your runtime will also increase. This means that increasing the number of steps is what is directly proportional to increasing the runtime. That's why instead of calculating the actual runtime, we can just calculate the number of steps your algorithm is going to require, right? If we can calculate the number of steps, then we can actually get a thought or an idea about the runtime that we are going to get, right? So that's why we need a function that calculates the number of steps. What do we need? We need we need a function that calculates the number of steps or the number of instructions, right? Okay, this function that we are talking about is basically the big O notation. Okay, the big O notation that we're talking about is basically the mathematical function that we talk about. Okay, and how does it work? So let's say you have an algorithm. Okay, let's say you have an algorithm. Okay, A1, and let's say it takes X number of steps. It takes X number of steps. Then basically the runtime of your function is what? It's order X, right? Basically what we are writing, we are saying that this algorithm is going to take how many X number of steps to execute, right? That we are writing. So basically what we can say, in other words, we can write that function of A1, basically this algorithm, okay, the runtime, the number of steps this algorithm will take is equal to what? Is equal to X. In other words, we can write this as order of X. It takes X number of steps. Okay. Our thing is, we cannot actually count the number of steps, right? You cannot make a counter variable to count the number of steps that you're going to write, right? We don't know about what statements are we are going to execute. We just need to know what steps can be, what is an upper bound of the steps. Okay, for this purpose, what we do, we take the input size as a parameter, right? We know that all the algorithms that we write are basically based upon the input that we're getting, right? Everything is based upon the input. If your input is large, the number of steps would increase. If your input is small, then your number of steps would not be that much big, right? So that's why the best parameter to choose, that will make everything unbiased, is the parameter, right? The parameters or the input size slash input size. Why? Because regardless of the machine, if the number of steps or the input size, okay, regardless of any machine, let's say you're a fast machine or a slow machine, but let's say your algorithm takes a lot of steps, when the input size increases, then it means that it might not be a very efficient algorithm, right? This means that input size will work as a very good parameter for judging the runtime. Okay, the input size n would be a very good parameter for measuring the runtime, best parameter for judging. Instead of taking the resources into account, what amount of RAM you have or what amount of speed of processor or anything else that you have. Instead of that, we judge the algorithms from a neutral point of view, from the perspective of the input size. Okay, when the input size increases, how much your runtime will increase, right? And that is basically the big O function. Big O function is a mathematical function. I'm repeating it again. It's a mathematical function, right? Now I'll just draw a graph for you to draw the differences between various complexities. Okay, let's make a graph. Okay, let's make a graph. Okay, so here we have what? Here we have the runtime. This is basically our time. Okay, and here we have what? Here we have the input size. Okay, This time can also be replaced by the number of steps. Basically, higher the bigger the input, and so bigger will be your number of time or bigger will be your number of steps. That's why time and steps represent basically the same thing. When we are talking about the runtime of an algorithm in terms of big O notation, we are basically considering the runtime and steps to be the same. Higher the number of instructions, higher the runtime. Okay, so we start off with the first thing, that is a straight line. Okay, if I draw a lot of straight lines, this basically means what? This means even when you are increasing your input, this means even when you are increasing your input size, your time remains constant. Your time remains same. Even on increasing the size of input, your time remains same. Hence, this is a constant time algorithm, or what you popularly known as order one. This is order one. Okay, and you can also write this as n. Basically, this is n, the number of input size. Okay, then let's say we have like this type of a linear type of a graph. Okay, what is this time complexity? We can see that our time runtime increases linearly with the number of steps. This means that when the number of steps increase by one, the runtime also increases. So we can write this one as order n. This is order n. Okay, then we have this might be what? This might be log x. Okay, we can see that it is between order one and order n, right? Okay, then we might have another function like sqrtx, right? Square root of x. That is also a valid time complexity. Okay, we can write sqrt of x. Okay, and then okay, and then you might have like order n square, right? And then you might have exponential time complexities, right? So these are various type of time complexity that we are basically going to cover. Okay. In generally when we are solving a problem, these are the complexities that we are dealing with. Okay, but there can be a composite function that involves a lot of this, like n log n. You might have heard n log n lies between n square and, let's say, this is n square. So n log n might pass in between like this. Okay, then let's say this one is n factorial or 2 to the power of n, because this is exponential. So this is how basically your graph works. Okay, this is basically the comparison drawn between various algorithms, the time taken by them, the steps taken by them with respect to the input size. Okay, so continuing this, we have three things. We have average case time complexity, we have best case, and we have worst case. And why do we even need them? Okay, simple सी बात है. If we have the worst case, we can get an upper bound, right? We can get an upper bound. This is basically the maximum time in which my algorithm will solve my problem, right? But then why do we need average case and best case? Each of them have their pros. Why we need to consider them? Okay, first of all, let's talk about the worst case complexity, and I'll also write a notation used for each of them. Okay, let's talk about the worst case. Okay, so worst case time complexity is generally known by the big O function that you know about, order whatever you write. Okay, this is basically the big O function. Okay, this is a big O function. So this gives you an upper bound to your runtime. Okay, this is used for upper bound, for upper bound. Okay, what upper bound means? Upper bound means that regardless of whatever the input size is, your problem will be solved by this algorithm within these many amount of steps. Let's say I write order n square. Okay, let's say I write order n square. It means that your algorithm will solve the problem within n square number of instructions or n number of square of steps. Okay, this means an upper bound. Your runtime will always be less than or equal to order n square. The number of steps required would be like this. This is the inequality that your runtime will follow. This is basically the worst case time complexity, and it is denoted by what? Big O notation that we generally use. So whenever we are solving a problem, we are always interested, what is the upper bound? कि हम maximum कितने time में इसको solve कर लेंगे, right? So to get an upper bound, we use the big O function. Okay. Then we go to the average case. Okay. Then we go to the average case complexity. Okay, average case in generally tells you, regardless of the input size, let's say it is big or it is small, what is the midway in between the the best and the worst. कि generally इतने में तो काम कर ही लेगा. What is the average case complexity? Let's say we take a distribution of a lot of inputs, then what is generally the time that your algorithm is taking? That will be denoted by an average case complexity. Okay, and this is denoted by theta. Okay, it is denoted by theta. Like this denoted by big O, it is denoted by theta function. Okay, and this will give you the average runtime. Okay, this has actually not a lot of significance, when you are writing an algorithm, or whenever we are discussing algorithm. Okay, but this gives you an overall a gist at how will algorithm work, how will algorithm perform. Then we have the last one, that is the best case. Okay, now best case gives you the lower bound. Okay, best case gives you a lower bound. As we said, the big O notation gives you an upper bound. The best case gives you the omega notation. This is denoted by omega. Okay, this is denoted by omega notation. Omega notation generally means that when we are talking about the best case time complexity, whatever is the best inputs that, we can solve the algorithm can solve the problem in the least amount of time. Okay. Considering an algorithm A, and we measure the runtime of best, average, and, worst case. If best gives, what is the least amount of time. Worst case gives you the, maximum amount of time that it will take, and average gives you the midway, right? So this gives you the lower bound, that your algorithm will at least take these number of steps, कि इससे नीचे तो ये नहीं जा सकता. This cannot perform better than this. Okay, it has to be at least this much amount of time. This gives the lower bound of runtime. Okay, this is basically the significance of each of them. The worst case gives you an upper bound, average case gives you a midway between range key so that you get an idea of the or the gist, and best case gives you a lower bound. So we can basically write an inequality like what? Your runtime is always something between order of whatever your algorithm is. Let's say let's say I'll write just order A1. So A1 basically is the algorithm. Okay. And omega of A1. So your runtime will always be within this range. Okay. This is basically the inequality that is followed. Right. Now let me give an example. Okay. A very good example. Okay. Let's take the example of linear search. Okay. We are talking about linear search. What is linear search? You need to find an element if it is present in an array or not. Okay. Let's talk about the worst case. The worst case complexity for finding an element in in an array would take n plus one number of steps. Let's say you have an element. Okay. Let's say you have an array like this, and you start finding your element, and you start moving from here, and you go, and you are not able to find your element. This means that you make n plus one number of iterations, right? You take n plus one number of steps. So this is the worst case that when you have iterated over the whole array and you are not able to find the element. This is basically the worst complexity that you will take to find out if an element is present in the array or not. So this is basically what this is the worst case. Worst case. Okay. Then what is the average case? Average case might mean that your element is somewhere in between the array. Let's say it is somewhere in between. So it will take about how number of it will take about number n by 2 number of steps or n by 2 plus 1 number of steps. Okay. So this is basically the average runtime in between. Right. So this basically means the average. Okay. Then we go to the best case. What is the best case of finding an element? The best case is that your the target element is present at the first index. Okay. The best case would be that you find your target element at the first index. Then you can directly stop your algorithm at that point of time. You can perform stop your search, and that will take that will take how many number of steps? That will take only one step. Okay, that will take only one step. You just compared it to this, and this is the best case. So you can see for the same algorithm, that is the linear search, we got different amount of runtimes. For worst case, we got n plus one number of steps. For average case, we got n by two plus one number of steps, and for best case, we got only one step. So that's why we need to assess a algorithm in this ways, that we take an upper bound and we get a lower bound. That okay, this is the basically the range in which your algorithm will always work. कि इस टाइम में तो ये काम कर जाएगा, एटलीस्ट इतने टाइम लगेगा और एट मैक्स इतना टाइम लगेगा. Okay. So this was basically about how these things are calculated and what significance they hold. Okay. This is the significance of best case and their notations. Okay. Notation हमने define कर दिए कि this is theta, this is omega. Okay. And this is big O, this is big O. Okay. Hmm. So now moving on, we'll discuss, what are the rules for, calculating time complexity. So generally, whenever we are talking about, calculating time complexity, we talk about big O notation. Why? Because big O gives you an upper bound. Key, this is the maximum amount of time that your algorithm will take to solve the problem. That's why we are always interested in the big O notation. So whenever an interviewer asks you, what the time complexity is generally meaning the big O notation. Okay, you have to tell the worst case time complexity that your piece of code will take. Okay, now what are the rules? What are the rules for calculating the big O notation function or the time complexity? The first thing is all the the initialization statements like variable declaration, okay, and if statements, print statements, okay, calling of a function, okay, and then what happened? Yeah. So now and what? Accessing some element in an array, accessing elements, okay, and a lot of things. Okay, so basically a lot of things have their time complexity as said to be order one. We say the time taken by these steps 1 2 3 that I've written is negligible in comparison to the actual number of steps. Okay, what we say that these things have negligible amount of time. These things have negligible runtime. Okay, we will neglect the amount of time that all these things will take. We'll just focus on the number of operations. Well, runtime. Okay. So how do we generally calculate the time complexity of some piece of code? It is generally determined by the for loops. Okay. So important thing, look out for while loops, while, do while, and for loops. And for loops, because these are basically the determining points of your algorithm, right? Let's say you haven't used any while loop, do while loop, or for loop. It might be possible that your time that you are only printing something, or it's just order one calculation. It takes fixed number of steps, right? So generally get the idea of the time complexity by looking at the while, do while, and for loops in a piece of code. Okay. So that is basically what we need to focus on. We generally, look at the while and the do while and the for loops, and other statements are considered to be running in order one time. Okay, their runtime is considered to be negligible, that they will not contribute towards the actual runtime, and we'll define our runtime in terms of how these loops are going to work. ओके हम देखेंगे कि जो इनपुट साइज है वो इन लूप में कैसे काम कर रहा है, हम उसको मेजर करेंगे, राइट? we'll neglect we'll assume that every other thing has a constant runtime, and that does not contribute to our actual time complexity, right? So remember, we need to focus on this. Okay, this is important. Okay, so now what I'll do, we just move on to some examples. Okay, now we have discussed, what are the rules regarding calculation. Let's move on to solving some very good examples and see how we actually calculate them. Right? Okay, so let me just move on to this. Okay, so we can see our first example. In the first example, we have what? I equal to 0, I less than 10, I plus plus print statement. So as we discussed, print statements don't take any time, right? So this loop will work for around 10 number of steps, right? So starting from example 1, let me write example 1. So it will start from 1 and 2, 3 till 10, right? So we can see that, regardless of the input size, this loop will always work for 10 number of steps. That's why we can say that this has a order 1 runtime. Okay. Another thing, see, whenever your loop is working for a fixed amount of time, fixed number of steps, then it's always order one until and unless the limit is actually is comparable to the size of input, right? Let's say you have n as 10 power of 5, okay, and your loop was working for 10 steps, then it's well good, it will be order one. But let's say your loop was working for around 10 power of 4 steps always, then we can see that n is comparable to the actual number of steps in the loop. In this case, we cannot say it's order one, right? Until unless we can say that this is 10 power of 5 is the is basically a lower limit, or it's not the upper limit. Let's say if n was way bigger, then we can say again it's fixed. But let's say when n and the number of steps, the upper threshold on n is actually is comparable to the fixed input number of steps, then we cannot say it's order one. Okay, remember this, it's very important. So here we can see that it's quite less. That's why it's order one. Okay, then we go to example number two. In example number two, we can see that we have I equal to 0, I less than n, and I plus plus. Okay, so we can directly see it's what, it's order n. Okay, right, it starts from one step and it goes up to n, so this one is order n. Okay, it was quite simple since printing statements don't take any amount of time. Okay, then we move on to the third example. Okay, the third example, we have I equal to 1, I less than n, I plus plus, I less than I mod 20 equal to 0. So we have an if condition here, right? So here comes a tricky thing. A lot of people, what they will do, that they will consider this one as and as an order n algorithm, right? You can see that it's I modulo 20, right? We can say that there is an if condition. A lot of people might not see the if condition and they would blindly say it's order n, but it's not order n. If you start your loop from 1, you can see that your loop will stop as soon as the value of I reaches 20. As soon as your I becomes 20, your loop will stop. This means that regardless of the value of n, your loop will always stop after 20 iterations. Your loop will always stop after 20 iterations. This means the time complexity of this piece of code is order 1, because regardless of the value of n, your loop is only working for 20 number of steps. Okay. Then we go to example number 4. Okay. So example number 4 is what? I equal to 1, I less than n, I equal to 1, I into I is less than equal to n, and I plus plus, right? Okay. So what is the runtime of this piece of code? So, yeah. Example number 4, we can see I starts from 1 and goes up to what? Goes up to I into I is less than equal to n and I plus plus, right? So we can see that our loop will stop as soon as the value of I into I becomes what? Greater than n, right? Our loop will stop. Okay. And we know that I is basically the number of steps that our loop is going to work for, right? So if I write this asymptotically, it will be I square less than n, or I can be written as what? I can be written as sqrt of n, right? So here we can see that the runtime of that of the example number 4 was actually sqrt n. The fourth example was working for a number of sqrt n number of steps, right? Then we go to the fifth example. We can see I equal to 1, I less than equal to n, and I into k. So we can see I starts from 1 and goes up to n, and every time we are updating the value of I by multiplying it by k, right? Okay. So here we can see that I have written a small constraint that k is always greater than 1. We'll see why I've written that. Okay. So for now, let's try to solve this problem. Okay. Sorry. Example number 5. So you start from 1 and you go up till I less than equal to n, and I is always multiplied by k. So initially you start from 1, then you become k, then you become what? K square. Then you become what? Then you become k cube, right? And then in this way you go up till some m number of steps, right? Okay, your loop will work until some m number of steps. As soon as k to the power of m becomes bigger than n, as soon as this condition will happen, your loop will stop, right? As soon as k to the power of m becomes greater than n, your loop will stop. Why? Because every time we're multiplying by k, and k is positive. Remember, k is greater than 1. Okay, so as soon as this happens, our loop will stop. And how many times has the loop worked? It has worked for m number of steps. So what is m? What is m? If we apply log of k on both the sides, we can say m is equal to what? Logarithm of k of n. So basically, the runtime of this piece of code is what? It is log n. Log n based k. Okay, the base is k. Okay. Now we go to the sixth example. In sixth example, again we can see it is what? I equal to n, I greater than equal to 0, and I by equal to k. So this time we are dividing by k. This time what we're doing? This time we are dividing by the value of k, correct? Example 6. So this is not very different from the previous example. Earlier we were multiplying. This time we are dividing things by k. And remember, k is always bigger than 1. This means your input n, or whatever the initial value was, it is bound to decrease every time, right? It will always decrease by k, by k. So initially, let's say you were n, then you go to n by k, then you go to what? N by k square. And this way you go until your n by k to the power of m becomes less than 0, right? As soon as this happens, you will stop. So again, we can rearrange the terms. As soon as n becomes less than k to the power of m, your loop will stop. Again, if we rearrange this will become what? M is what? Log of n, right? Base k. So again, the same runtime we are getting. So we can see how different implementations can have same runtime. Okay, this is also log n. Now we go on to the seventh example. Okay. Okay. There's something that we can see. Solve for 5 and 6 when k is less than 1. When k is less than or equal to 1. So here's the tricky part. Remember, if the value of k is 0, your update will always become 0. Let's say तुमने 1 से start किया और तुम 0 से बार बार मल्टीप्लाई कर रहे हो, will your value increase? अगर 1 था और 0 से मल्टीप्लाई कर दिया, it will always remain 0. चाहे मैं जितनी बार मल्टीप्लाई कर लूं, your loop will never stop. It will always be 0. How many number of times run your algorithm? So that's why in case when the value of k is less than 1, let's say it's 0 or 1, सिंपल सी बात है, अगर 1 से डिवाइड कर रहे हो या 1 से मल्टीप्लाई कर रहे हो, तो हमारा वैल्यू जो i का वैल्यू है वो अपडेट नहीं हो रहा है, वो वही रहेगा. लेट से तुमने 1 से स्टार्ट किया तो 1 का 1 ही रहेगा, और अगर लेट से तुमने n से स्टार्ट किया डिवाइड कर रहे हो तो n का n ही रहेगा. और सिमिलरली गोज विद k. अगर k 0 है तो भाई सिंपल सी बात है, तुम्हारा मल्टीप्लिकेशन 0 हो जाएगा एंड योर आइटरेटिव वेरिएबल will not increase, right? So in case, for example, 5 and 6, whenever the value of k is 1 or 0, the runtime would be indefinite. Your loop will never stop. It will be infinite number of times. Your loop will not stop, right? वो stuck हो जाएगा, right? Then we go to the example number of 7 and example number 8. Let's talk about example number 7. So here we have what? I equal to 1, I less than equal to n, I plus plus, for j equal to y, j less than equal to n, and j plus equal to y. Okay. This one is actually quite tricky. अबे tricky क्यों है? ये देखते हैं. एक बार आप इसको अच्छे से देख लो. Okay. So I hope सबने देख लिया होगा. राइट right. अब आते हैं इसको सॉल्व करने पे. याद रखना, i equal to 1, i less than equal to n, और जो अंदर वाला लूप है दैट इज j equal to i and j is less than equal to n and j plus equal to i. हर बार प्लस i हो रहा है, याद रखना. ओके. अब आते हैं इसको सॉल्व करने पे कि इसका रन टाइम एक्चुअली में है क्या. ओके. सो या सो पे अटेंशन, बहुत ध्यान से अटेंशन रखना अपना इस वाले के लिए. ओके. तो दिस एग्जांपल नंबर 7. ओके. So let's say your outer loop is going to work for n times. As we know that the outer loop is what? It starts from 1 and goes up to n, and every time it is I plus plus. So the outer loop is taking what? Outer loop is taking n time. Okay. Outer loop n time काम कर रहा है. Okay. अंदर वाला loop कितनी बार काम कर रहा है? Okay. Let's start from 1. When the value of I is 1, okay. Whenever the value of I is 1, so how many times this will work? This starts from 1 and it becomes 2. एंड अंटिल इट बिकम्स एन। सो हम क्या कर रहे थे, हम कर रहे थे व्हाट, जे प्लस इक्वल टू आई। हम हर बार जे को बाय आई अपडेट करें, तो इनिशियली हमारा आई वन था, तो दिस विल टर्न फॉर एन टाइम्स। ओके, जब मेरा आई की वैल्यू, जब मेरे आई की वैल्यू 2 होती है तो क्या होगा, दिस टेक्स 1, देन दिस गोस टू 3, देन 5 एंड अप टिल एन। यहां पर देख रहे हो जब 2 हमने चूज किया तो ये +2 +2 बढ़ रहा था। ओके, फिर लेट्स से मेरा जे की आई की वैल्यू 3 हो गई। जब आई की वैल्यू 3 हो गई, दिस वर्क्स फॉर 1, देन इट गोस फॉर 4, देन इट गोस टू 7 एंड इट गोस टू एन। Okay. In a similar way, when the value of I is 4, it becomes what? I, 5, and then 9, and in this way. So आप देख सकते हो कि हर बार क्या हो रहा है, आउटर लूप के हिसाब से अंदर वाला लूप डिटरमाइन कर रहा है कितने स्टेप्स लगेंगे। When the value of I was 1, it worked for n number of steps. When I became 2, it worked for n by 2 steps. When I became 3, it worked for n by 3 steps. अगर आप इसको निकालोगे ना, ये n by 3 आएगा basically. This is working for n by 3 steps. So what we can see is that here, when I equal to 1, your inner loop works for n times. I equal to 2, your inner loop works for n by 2 number of times. I equal to 3, it works for n by 3 number of times. And in this way we can go on, right? So basically, we can see that these are basically the steps that will determine our time complexity. जो ये हमने सीक्वेंस लिखा है ना, ये हमारा एक्चुअल नंबर ऑफ स्टेप्स भी डिनोट कर रहा है, राइट? सो वी कैन से दैट आवर एक्चुअल रन टाइम इज व्हाट, इट इज द समेशन ऑफ n by I, right? Starting from I equal to 1 up till n. So हमारा रन टाइम क्या है, वो बेसिकली यही है, द समेशन ऑफ दिस थिंग। बट ये जो मैंने लिख दिया, ये आखिर मतलब क्या है, इसका मीनिंग क्या है? विल जस्ट ओपन दिस दिस समेशन। ओके, we can write this as, we can write what is happening. Okay, so we can write this thing as what, n plus n by 2 plus n by 3 and up till n by n, right? And n by n is basically 1, so I'll just write 1. Okay, plus 1. Okay, let's say n by n ही ले लेते हैं। Okay, now what I can do, I can take n common from all these terms, right? मैं n common ले सकता हूँ। So when I take n common, this becomes what, 1 plus 1 by 2 plus 1 by 3 plus up till 1 by n. Okay, now we are getting something. We know कि ये भाई n तो ठीक है, n तो अलग हो गया। How do we evaluate this thing? This thing is basically, if you go and search it out, this is actually a very well convergent series. This is actually a harmonic series. And for it has been proved that for large values of n, for large values of n, this summation actually, this summation that we are going to write, okay, this converges to around log n with some constant. If you go and search it out, this constant is basically the Euler-Mascheroni constant, and this value is around 0.5. So this is actually negligible. If you see, if you try to go and search upon this, the proof of the series, you'll find out that the convergent value of the series is log n plus some constant, and that constant basically Euler-Mascheroni constant, and the value of that is around 0.5. So that's negligible. So we can see that this whole series converges to around log n. Okay, and that's quite fascinating because now we can see that this is the dominating part. This is the dominating part. So hence wise, our time complexity becomes what? It becomes n into log n. N into log n. So your, for example, number of 7, the runtime was what? Your runtime was n log n, right? So this was a nice one. Okay, let's go to the next case. Next we have what? Question example number 8. So I equal to 0, j equal to 0, I less than n, and j less than n. So I less than j, I plus plus. So we can see that there is an if condition. At the same time, now what do you think that what will be the time complexity of this approach? We can see that every time one of the variables is increasing, and as soon as one variable reaches the end, this will this will stop, right? This will stop. Correct. So even without lifting pen, we can say that first j will cover that element and then I will cover that element. So every element is being covered by two variables, by two, basically, yeah, two pointers, and that's why the time complexity of this piece of code will be what, order n. This will also be order n. Okay, now we go to example number 9. And now we have something for us. In example number 9, we can see that I have a while loop within a while loop. Now you can try to pause the video for some time and solve this on your own कि इसका टाइम कॉम्प्लेक्सिटी कितना आएगा. A lot of people get confused that whenever they see two loops, what they do, that they think, okay, दो loops है तो it's order n square. That is where I always say, do not be misguided by two loops. These things are very deceptive. Always look for conditions, that how variables and how everything is getting updated. What are the variables that are contributing towards the runtime? What are the parameters that basically decide that how many times failure algorithm take? Right? Always look out for them. ओके, डू नॉट बी मिसगाइड बाय कि कितने लूप्स हैं. मैं अंदर 3, मैं ऐसा भी कर सकता हूँ कि मैं एक के अंदर 5 लूप लिख दूं, बट फिर भी उसका टाइम कॉम्प्लेक्सिटी ऑर्डर 1 आए. So always be on lookout for these things, these tricky things. Okay, here we can see that we have j less than n, and while I less than j, I plus plus. So what I do, I can say, that initially both of them are zero. Initially both of them are basically start from zero, and what I do, I keep on increment j, and whenever my I becomes less than j, while my I less than j, I do what, I plus plus. So we can see that both the pointers are actually incremented in the forward direction, and none of them are repeating what they have covered. ऐसा तो है नहीं कि भाई I जो है जिसने उसने मान लो लेट्स से तुम्हारा कोई वैल्यू कवर कर ली, अगर लेट्स से I की वैल्यू 3 हो गई है, I दोबारा 2 पे तो जाने नहीं वाला. So we can see both of these variables are always going in the incremental direction, and वो भी simultaneously. When j increases, then we have a inside while loop, while I less than j, I is basically I plus plus. So we can see कि दो loop हैं, फिर भी each of them is going in the incremental direction, and everyone gets a bit only one time, right? That's why the time complexity of this piece of code is also what? It's order n. This is also what? Order n, because each I and j are incrementing only one time, and that too also in the forward direction. ऐसा नहीं है कि हर एक I के लिए j n time चल रहा हो. We can see that both are moving simultaneously, okay, parallelly. That's why we can say that the runtime is order n. Okay, then we go to the example number of 10. Example number 10. Okay, so example number 10 is what? I equal to 1, I less than equal to n, and I plus plus, then j equal to 1, j less than equal to y, and j less than equal to j into equal to 2. So I want everyone ki you just pause the video for some time and try to calculate the runtime for this piece of code on your own. Okay. Okay, so I hope you have tried it out. So now let's discuss. This is actually also a tricky one. ये भी tricky है. Now let's try to analyze ki how is this loop working. We can see that outer loop again we have I equal to 1, I less than equal to n, I plus plus. Okay, the inner loop is very tricky. Inner loop starts from 1 and it goes up to less than equal to I, and every time we are multiplying j by 2. Every time there is an exponential increment. And every time it becomes, let's say, 1, then it becomes 2, then it becomes 4, 8, 16, 32, and this is how it's basically increasing until the value of j does not exceeds the value of I. So what we can do, we can write, let's say when value of I is equal to 1, okay, your loop will work until 1. Very good. When the value of I is 2, it works for 1 and 2. Okay, let's say the value of I is 3. Again, what will happen? Again, it will work for 1 and 2. Remember, until your j does not exceed the value of I, and always we are multiplying by 2. When I becomes 4, it will go 1, 2, 3, 1 to 4, 1, not 3, will go to 1 to 4. Okay, in this way we are going to increase. So we can see जो अंदर वाला loop है वो it is always taking what? It is always taking logarithmic number of steps. So what we can see, for each I, the inner loop works for log I steps. Correct? This is what? For each I, the inner loop works for log I number of steps. Okay. So अब इसको फिर calculate कैसे करें? So we can see basically हमें sum up करना है. So when I is 1, we can say it's log 1. Okay, when I is 2, it will take log 2. Okay, this is basically a summation. This is basically a summation of log I starting from 1 and going up to n, and this is basically base 2 because हम 2 से multiply कर रहे थे, right? So this will be what? This will be log 3 and going up to what? Up to log of n. Okay, ये series है. अब इसको कैसे calculate करें? We know the property of log. What is the property of log? Log of a plus log of b is what? Log of a into b. So हम क्या करेंगे? हम इसको converge कर देंगे. This will be what? Log of 1 into 2 into 3 into 4 up till into n. And what is this? And what is this thing? This is basically n factorial, right? So a time complexity will be log of n factorial. Nice, right? This is log of n factorial. Okay. So I hope you understood this. Let's move on to the next example. You can take a pause and you can go up, you can rewind so that you get the computation कि हमने कैसे calculate किया. Okay. Next we have example number 11. And yeah, we have what? P equal to 0, I equal to 0, I equal to 1, P less than equal to n, I plus plus. So here we can see we have some change. This time I is not the deciding factor, right? This time we have actually changed. Here the important condition जो कि हमारा loop बचा के रखता है, that is not dependent upon I, it is dependent upon the value of P. Remember this. I को मत देखो, blindly follow मत करो कि कौन सा तुम्हारा variable है. It might be possible that the decision making condition has some other variable rather than the iterative variable. In this case, we can see that there is P and P is the deciding factor, right? And every time what we are doing, we are increasing the value of P by I, right? अब इसको जरा समझ के देखते हैं. Okay, so what will happen? What will happen? P is initially 0, I is also 0, and every time what you do, you increment the value of I and you also add the value of I to P. So initially P क्या होगा? Initially P 1 होगा, 0 होगा. Then what we do? I becomes 1 and we add this 1 to P. P becomes 1. Now I becomes 2. When I becomes 2, we'll add 2 to the P and P will become what? 3. Right? When I becomes 3, we will add 3 to P and P will become 6. So you can see something. What we are doing, every time basically we are adding I to P. So ये कब खत्म हो जाएगा? Whenever the summation of I exceeds N. We can see P क्या स्टोर कर रहा है? P is basically storing summation of N. Summation of I, right? P stores summation of I. In other words, I can just write P is basically summation of I. Okay, so as soon as P becomes P, the value of P exceeds N, we'll stop our loop, right? So when we are writing this, summation, so what we can say, it is what? We'll start from 1, then we'll 2, then this is 3, then going up to I steps. Let's say at ith step, our loop stopped working. So ये क्या होता है? This series we have already seen a lot of times. This basically is the summation of first n natural numbers. So this basically summation is equal to what? I into I plus 1 बाय टू. ये कोई रॉकेट साइंस नहीं, ये आपने मैथ्स में पढ़ा हुआ है, बहुत बेसिक 10th 12th क्लास की चीज है, 10th 11th क्लास की चीज है. नाउ विल जस्ट गो टू दिस. सो व्हेन I into I plus 1 by 2 becomes greater than n, we'll stop. Okay. Now in other ways we can also see that this is what? This is a quadratic term. यहाँ पर क्या है? यहाँ पर dominating factor क्या है? If we open out this term, we can see this is what? I square plus I greater than equal to 2n. ये ऐसी क्वेश्चन कुछ बनेगी, right? So here we can see the dominating factor is I square. I is not a dominating factor. I square is a dominating factor. याद रखना. Whenever we have multiple things in a time complexity, the dominant one is the one that decides the time complexity. Let's say आपका अगर time complexity होता है n log n plus n square. अगर मान लो आपका time complexity कुछ किसी ने लिखा होता इस टाइप का, ओके, यहां पर ये डोमिनेंट फैक्टर है, याद रखना. दिस इज अ डोमिनेटिंग फैक्टर. इसके हिसाब से डिफाइन होगा कि आपका एल्गोरिथम कितने स्टेप्स लेने वाला है, राइट? सो वील अगेन मूव बैक. सो हियर वी कैन सी दैट इज व्हाट? I square plus I is greater than equal to 2n, or we can say I square is greater than equal to n. Again, we can see that, taking square root on both sides, I is what? SQRT n, and it is also the number of times our loop is working. So that's why the time complexity is what? It's square root of n. Okay, right? I hope you understood this. Okay, let's go to the second next example. Okay, we have what? We have a 12th example. Okay, so now we have what? From the above example, suppose you are passed with the values of P and I. Okay, suppose from the previous example, we say that we are passed with the value of what? P and I. So now our loop will work how many times? J equal to 1, j less than equal to I, and j into equal to 2. ठीक है, आई होप यू अंडरस्टैंड कि ये कैसे काम कर रहा है. जो प्रीवियस वाला एग्जांपल था उसमें से हम आई की वैल्यू उठाने वाले हैं कि जो आई की एंड में वैल्यू आई होगी उसको यूज करने वाले हैं इस वाले एल्गोरिथम में, राइट? यहाँ पर क्या है? योर लूप इज स्टार्टिंग फ्रॉम 1 गोइंग अप टू आई एंड एवरी टाइम वी आर मल्टीप्लाइंग बाय 2. सो हाउ मेनी टाइम्स विल दिस वर्क? Okay, so we can see that the value of I was what? SQRT n, right? And the J loop is going up to value of I, and every time we are multiplying by what? By 2. So we will stop, let's say at some k iteration, as soon as some 2 to the power of k becomes bigger than I. As soon as this will happen, हमारा जो loop था वो बंद हो जाएगा, right? So what I can say, k is basically what? K is the number of steps that मेरा जितना मेरे algorithm मेरा काम करेगा, जितनी देर मेरा loop चलेगा, right? So if I take log on both sides, k will be equal to what? Log 2 based I. And what was I? I was SQRT n. So this becomes log of SQRT of n. So the runtime of that piece of code is what? Log of SQRT of n. Remember, this is what? This is order of log SQRT n. ये हो गया हमारा 13 example number 12. Right? Now let's move on to the 13th example. ठीक है, काफी सारे एग्जाम्पल मैंने लिखे थे. Okay. Now we come to this part. Here we can see I starts from 1, goes up to j is m, and I less than equal to j by equal to 2. So we can see already आप देख सकते हो कि हर बार j by 2 डिवाइड हो रहा है. इसका मतलब लॉगरिथमिक टाइम कॉम्प्लेक्सिटी आप जा रहे हो कि एवरी टाइम यू आर डिवाइडिंग बाय 2. तो लेट्स से m था, फिर m by 2, फिर m by 4, फिर m by 8, m by 16, ऐसे से होगा. And every time your loop is out, that j is updating. Every time your inner loop is working for how many times? It is working n times, right? That k loop is working n times. Okay. So यहाँ देखते हैं. Okay. So every time your loop works, so basically पहले m का m step आया, फिर m by 2 step आया. So your outer loop is working for log m number of times, correct? It is working for log m number of times. At the same time कि जितनी बार ये outer loop चला है उतनी बार the inner loop is also working for n number of times. For every iteration of the outer loop, inner loop works for how many times? N times. So that's why the time complexity becomes what? N into log of m. और बहुत सारे लोगों ने ये पहचान लिया होगा that this is very similar to a lot of questions where you use binary search. Okay, so here we can see the time complexity is what? N into log of n. हम देख सकते हैं कि the outer loop was working for log m times कि हर बार by 2 कर रहा था, तो this is log 2. and for every iteration of the outer loop, the inner loop of k works for n times. So n into log m, that is the final runtime of this piece of code, the time complexity of this piece of code. Okay. Then we move on to the final example of our show, and that is basically a very quite famous example. We can see that L starts from 1, R goes up to N. Then we have a merging function. Merging function starts from L and goes up to R. We can see that the merge function has some loop that starts from L and goes up to R and has some constant statements. And then we have a function known as divide. Divide also starts from L to R, and we calculate L plus R by 2, basically the mid. And then for each value of L to M and M to R, we call merge. Right? जो आप कोड अभी देख रहे हो, दिस इज एक्चुअली द कोड ऑफ मर्ज सॉर्ट. ओके, ये कोड जो है ये बेसिकली बैकबोन है मर्ज सॉर्ट का. हम इसमें अगर फंक्शन कुछ स्टेटमेंट्स और ऐड कर दे कंपैरिजन के, दिस विल बिकम मर्ज सॉर्ट. बट इन जनरल व्हाट आई हैव रिटन हियर इज बेसिकली द फेमस टेक्निक ऑफ डिवाइड एंड कॉन्कर. ओके, ये होता है डिवाइड एंड कॉन्कर. अब आओ इसका रन टाइम एक बार एनालाइज करते हैं. ओके, सो वी कैन सी दैट योर डिवाइड फंक्शन विल वर्क हाउ मेनी टाइम्स. हम देख सकते हैं कि इट इज डूइंग व्हाट इट इज. ओके, मैंने एक चीज यहाँ पर लिखनी भूल गया. ओके, लेट मी चेंज दिस थिंग that we also call okay, this merge step will only for L to R. Okay, this will be basically L, M and R. Okay, and what we do, we call, yeah, we call the divide function again and again for L to M, and yeah, divide M to R. Okay, now it's perfect. Okay, so we can see that whenever the divide function is called, every time it's dividing a search space by 2. इनिशियली मान लो 1 और n था, ठीक है, तो तुम्हारा पहले क्या होगा, 1 से लेके n by 2 और n by 2 से लेके n तक ये डिवाइड हो जाएंगे. उसके बाद क्या होगा, एवरी टाइम योर सर्च स्पेस इज गेटिंग हाफ्ड बाय 2 by 2 by 2. इसका मतलब योर डिवाइड फंक्शन इज गोइंग फॉर हाउ मेनी टाइम्स, इज गोइंग टू वर्क फॉर लॉग एन नंबर ऑफ टाइम्स. क्योंकि जैसे आप एक 1 का फंक्शन रीच करोगे, 1 का साइज रीच करोगे, मैंने वो कंडीशन यहाँ पर लिखी नहीं है, आई शुड हैव मेंशनड इट, बट अज्यूम कि यहाँ पर 1 की कंडीशन लिखी हुई है दैट योर वैल्यू ऑफ l बिकम्स ग्रेटर देन और इक्वल टू r. ओके, उस टाइम पे आप स्टॉप कर जाओगे, राइट. सो we can see that your the divide function will take how many steps that will take divide takes log of n number of steps, right, क्योंकि 1 से लेके n तक का था, right. And whenever we are calling divide function, for each divide we're also calling a merge function, right, we're also calling a merge function, right. अब merge function कितना टाइम लेता है, we can see that merge function is a linear function जो कि L से R काम करेगा, इसका मतलब n टाइम्स काम करेगा, L से R जो भी रेंज रही होगी उसके लिए काम करेगा. So we can see that for every divide call our merge function will work for linear time. और we can say that initially इसको अगर मैं लिख के दिखाऊं, so this will be like this कि पहले n था, फिर ये 2 हिस्सों में डिवाइड हुआ, एंड ईच, ठीक है, 2 हिस्सों में डिवाइड हुआ, याद रखना मैंने इसको L से R और R से M चलाया था, दैट्स व्हाई इसको 2 स्टेप में चलाया. लेट मी राइट इन द फॉर्म ऑफ अ ट्री. इनिशियली मेरा प्रॉब्लम n साइज का था, उसके बाद मैंने क्या किया, इसको 2 प्रॉब्लम्स n by 2 साइज में डिवाइड कर दिया, करेक्ट. उसके बाद ये और फर्दर डिवाइड हुए n/4 में और n/4 में, और ये भी n/4 में और ये भी n/4 में, and in this way you will go on. So we can see that the depth of this tree is what, इस ट्री का डेप्थ क्या जाएगा, that will be log of n, right. क्योंकि सिंपल सी बात है, log of n के बाद वो 1 का साइज रीच कर जाएगा. और अब देखते हैं कि हर एक लेवल पे कितने ऑपरेशन किए, राइट. आप पहले लेवल पे देखो, यहाँ पर n स्टेप्स हुए, राइट. सेकेंड लेवल पे देखो, n/2 plus n/2 is what, it is again n, right. उसके बाद n/4 plus n/4 plus n/4 is basically 4 times of n/4, it is again n. So we can see that for each depth the amount of time our merge is, or the number of statements our merge is working for is basically n. So we can see that for every depth our merge function works for n time. So overall time complexity will again become n into log of n. और इस तरीके से आपकी फेमस मर्ज सॉर्ट की टाइम कॉम्प्लेक्सिटी निकलती है. This is order of n log n, right. So yeah, so that is how it works. Okay, and this was all for the examples, guys. So हमने 14 examples discuss किए. I hope everyone liked it. Okay, एक बार फिर से इसके go through कर लेते हैं. So starting from the first example, I would also like कि अगर आपको और कुछ examples अच्छे लगे, you can go ahead and try out. You can also go ahead and look out a very famous book. You might have heard about Data Structural Algorithms by Narasimha Karumanchi. Okay, it is a very good book for beginners, for everyone who's looking out to study data structural algorithms. The chapter on time and space complexity is a very good one. It's a very detailed one. बहुत अच्छे examples उसमें. You can go and try out some examples on this, and you can also, I think, मैंने काफी कुछ cover करने की कोशिश कर ली है already. The examples were, I think, quite good enough. So yeah, So that was all for the guys. I hope आपको समझ में आ गया होगा कि how we calculate the runtime, what are the various notation that we use, and what do they represent, what is the significance, and what are the rules for calculating time complexity and space complexity, right? So I think that is all for today, guys. And this marks the end of our part two. And now we have completed the discussion on time and space complexity. I think we have covered all of the things that that you need to know before starting off, before kicking off the data structures and algorithms. Okay, ये complete हो गया है. And from next video onwards, we'll take up some other topic. Let's see कि वो topic क्या होगा. And here part two ends. Thank you for tuning in and keeping your patience. And I hope that we'll see each other again in very soon. Until then, bye bye guys. Signing off. Meet you in another video. Bye bye.